For decades, automotive safety relied on cause and effect. A metal gear snaps, a brake line ruptures, the machine seizes, and a crash follows. Engineering standards, specifically the widely used ISO 26262, focused entirely on this chain of events. The logic was straightforward: prevent the parts from failing, and you prevent the accident. But put an autonomous vehicle on the road, and that logic falls apart. You can have an engine in perfect condition, cameras streaming pristine 4K video, and LiDAR arrays spinning flawlessly, yet the vehicle still gets into a crash. Zero mechanical faults, zero electrical faults. The old rules of automotive safety simply cannot explain what went wrong. This gap in logic required a new framework, called ISO 21448, better known as SOTIF, the safety of the intended functionality. SOTIF is designed specifically for situations where a system works exactly as engineered, but still fails due to a performance limit or an unexpected environmental trigger. Autonomous safety relies on ensuring a mathematically perfect system survives a chaotic, unpredictable reality. SOTIF relies on a verification and validation framework, operating as a continuous cycle. Verification is defensive, proving the system handles known risks, like slowing down in rain. Validation is exploratory, using real-world data to hunt down unknown risks. Whenever validation uncovers a new hazard in the real world, that data feeds back to the verification side to become a new design requirement. The entire framework operates as an ongoing search and rescue mission, systematically finding dangerous unknowns and transforming them into safe, manageable knowns. Finding those unknowns requires testing the physical hardware. Every sensor on a car, whether a camera, a radar system, or a laser, is bound by the laws of physics. This diagram shows radar multipath. A radar wave bounces off a metal guardrail and reflects back. Because the signal took an indirect path, the computer hallucinates a ghost target in its own lane, triggering phantom braking. These hardware limits are compounded by the AI software interpreting the data. Machine learning models are highly vulnerable to what engineers call confidence pitfalls. An AI might state with 99% probability that the path is completely clear, but if the training data lacked that specific rare object, the high percentage doesn't mean the computer is correct. It just means the computer is highly confident in its own mistake. When you combine bouncing radar waves with overconfident algorithms, the greatest danger to an autonomous system is its own misinterpretation of the physical world. To map out these misinterpretations, validators categorize extreme anomalies into two distinct buckets: edge cases and corner cases. An edge case occurs when a single operational variable is pushed past its physical threshold. Think of a car driving into complete, pitch-black darkness. Because an edge case isolates just one extreme variable, the boundaries are relatively simple to define. Engineers can write a clear rule to handle it, like slowing down or safely pulling over. A corner case is entirely different. This Venn diagram shows multiple normal variables overlapping: a low sun angle, wet asphalt glare, and a pedestrian in dark clothing. Combined, they render the human invisible to the car sensors. Catastrophes on the road rarely stem from a single extreme event. They emerge from the silent, complex alignment of ordinary variables. All of this testing and categorization culminates in the final output of the Clause 9 process, the verification and validation strategy document. Engineers acknowledge that an absolute guarantee against every possible crash is scientifically impossible. Instead, the strategy provides a rigorous, evidence-based argument that the vehicle is safe within its mathematically defined limits. Crucially, it functions as a living document. As the AI drives more miles and inevitably encounters new, undiscovered corner cases, the safety parameters must continuously evolve to absorb that new data. In the age of artificial intelligence, safety requires a relentless, ongoing commitment to mapping the unknown.